Let's dive right into this explainer. Today, we are looking at something absolutely fascinating, the hidden, chaotic complexities of the applications that we literally use every single day. Look, when we open up our favorite apps, we expect them to be incredibly fast, totally reliable, and perfectly up to date. We unconsciously assume that we are interacting with a single, instantaneously updated database somewhere in the cloud. But the reality? Well, that is a fragile illusion. Today, we're going to pull back the curtain on distributed databases and explore the very real, very frustrating anomalies that occur when that illusion completely breaks down due to replication lag. It's like a giant puzzle, and we're going to see what happens when the pieces don't quite fit together in time.
Here is our roadmap for today. First, we'll cover the replication lag problem. Then, we'll tackle 3 distinct user frustrations: reading your own writes, moving backward in time, and violations of causality. And finally, we will wrap things up with designing for lag.
Section 1. The replication lag problem. To understand why things go wrong, we have to understand how modern systems are built. Modern online services face a really unique challenge. Their workloads consist overwhelmingly of reads, with only a tiny percentage of actual writes. Think about how many times you idly scroll through a social media feed compared to how often you actually sit down and type out a status update. To handle all of that massive read traffic without literally melting the main servers, engineers use a read scaling architecture. We add many follower database nodes whose sole dedicated job is just to serve data to users who are reading it. But here is the million-dollar question. How do we get the original data from the leader node to all of those followers? Well, if we use synchronous replication, the leader node actually stops and waits for every single follower to confirm, yes, I got the data, before telling the user the operation was a success. Now that's incredibly reliable, but it is also exceptionally fragile. If just a single follower blips offline for a second or the network hiccups, the entire system grinds to a halt. Realistically, we just can't do that at scale. So we have to use asynchronous replication. The leader sends the data out to the followers and immediately moves on with its life. It's incredibly fast, it scales beautifully, but it introduces a massive catch. It is highly prone to lag.
Because we are relying on this asynchronous replication, running the exact same query on the leader and on a follower at the exact same millisecond might yield entirely different results. This temporary state of inconsistency is what we in the industry call eventual consistency. The promise here is that if you just stop writing new data and just wait, the followers will eventually catch up. But, eventually is a very dangerous word in software engineering. There is theoretically no limit to how far a replica can fall behind. That delay, that is replication lag. In normal happy path operation, we are talking about a fraction of a second. You don't even notice it. But under heavy load, network partitions, or resource contention, that lag can grow to seconds or even minutes. And when that happens, eventual consistency stops being a neat little theoretical concept and turns into a real-world nightmare for your users.
Section 2. Reading your own writes. Let's make this concrete. Imagine you are in a heated debate on an online forum. You type out this brilliant, perfectly reasoned, paragraphs-long comment. You triumphantly hit submit, and the page instantly reloads. But your comment isn't there. Where did it go? Did the system eat it? Was it moderated instantly by a bot? Do you have to type all of that over again? As a user, you aren't just confused in this moment, you are incredibly frustrated, maybe even ready to close the app forever. It completely breaks your trust in the system.
Behind the scenes, the mechanics of this particular failure are actually surprisingly simple. When a user submits their comment to the leader database, the write is completely successful, and the leader immediately sends a big thumbs up, an OK, back to the user's browser. But remember our architecture? We have a read-heavy system, so when the user's page instantly reloads to view the updated thread, that read query is routed over to an asynchronous follower just to balance the load. Because of replication lag, that specific follower hasn't actually received the new comment from the leader yet. It is completely unaware of it. It's serving stale data. So the database essentially tells the user's browser, hey, I have absolutely no record of this comment you're looking for. The data isn't lost at all, not even close, it just hasn't arrived at that specific destination yet.
So how do we fix this? To solve this, we need a specific, strong guarantee called read after write consistency. This is essentially a promise from the system that reassures a user they will absolutely always see their own updates immediately. We can achieve this through a few clever routing techniques. For instance, if it's something only the user can edit, like their own personal profile settings, we can just bypass the followers entirely and always route those specific reads directly to the leader node. Problem solved, right? But what if everything is editable by everyone? In that case, we can track update times.
For example, for exactly 1 minute after a user updates any piece of data, we route all of their subsequent reads straight to the leader. Or, we could even have the client app itself remember the logical timestamp of its most recent write. When the app asks a replica for data, it includes that timestamp, essentially giving the database an ultimatum. Do not answer my query until your data is caught up to at least this exact moment in time.
Section 3. Moving backward in time.
Now picture this scenario, which is arguably even more confusing. You refresh a web page and you see a brand new comment from a friend. Great. A moment later, you swipe down to refresh again just to see if anyone replied, and the comment is completely gone. The data was literally just there, and then it vanished. It feels as if time just moved backward, making you seriously question your own sanity, or making you wonder if your friend suddenly panicked and deleted their message.
This time travel illusion occurs because of how our load balancers handle sequential queries from a single user. Think of the load balancer like a roulette wheel. When the user refreshes the page the very first time, the system routes their request to a fast, fully up-to-date follower, which successfully returns the newly written comment. But on that second refresh, the load balancer randomly routes the request to a completely different follower, one that happens to be suffering from greater replication lag. This slower follower returns 0 results because, well, it hasn't seen the update yet. Because the user's queries bounce from a fresh replica over to a stale replica, they actually observe the database at an earlier point in time on their second read than they did on their first. They literally went back in time.
To prevent this jarring, sanity-questioning experience for our users, we require a concept called monotonic reads. Now, this is a lesser guarantee than absolute system-wide strong consistency, but it is way, way stronger than vague eventual consistency. Monotonic reads specifically promises that if one user makes several reads in sequence, they will not read older data after having previously read newer data. Simply put, once they have seen the future, they won't be sent back to the past. Time will only ever move forward for that specific user.
The solution here is actually remarkably straightforward once you think about it. We have to stop routing requests randomly. To achieve monotonic reads, we just ensure that an individual user always reads from the exact same replica. Instead of relying on a random load balancer roulette, the system selects a replica based on a hash of the user's ID. By tying the user to a specific node, as long as they keep asking that exact same replica for data, time only moves forward. It might be lagging, but it's lagging consistently. The only edge case we really have to worry about here is if their assigned replica literally crashes. In that scenario, they obviously have to be rerouted to a new node, but the system must meticulously ensure that the new node contains data at least as recent as their last read before serving them, otherwise we're right back to time travel.
Section 4. Violations of Causality.
The source text for this topic provides a really wonderful dialogue from a Terry Pratchett novel to illustrate this next anomaly, and it hits the nail on the head. Mr. Poons asks, "How far into the future can you see, Mrs. Cake?" And Mrs. Cake replies, "About 10 seconds usually, Mr. Poons." There is a strict, undeniable causal dependency here. Mrs. Cake's answer mathematically and logically cannot exist without Mr. Poons' question happening first. She hears the question and then she provides the answer. Cause, then effect.
But what happens when we distribute a conversation exactly like this across a partitioned or sharded database architecture? Imagine a third-party observer is listening to this conversation by querying follower databases. Mr. Poons' dialogue is written over to shard 1, while Mrs. Cake's dialogue is written to shard 2. Now let's say shard 2 is replicating very, very quickly, so the observer's query easily reads Mrs. Cake's answer. But shard 1, it has a much longer replication lag. By the time the observer reads shard 1, Mr. Poons' question still hasn't arrived, so the observer literally hears the answer before the question is even asked. Such psychic powers might be impressive for a fortune teller in a fantasy novel, but I promise you, they are disastrous for database integrity. The causal relationship has been completely shattered.
To stop our databases from acting like psychics, we need a guarantee known as consistent prefix reads. This basically ensures that if a sequence of writes happens in a certain causal order, anyone reading those writes will see them appear in that exact same order. This sounds so incredibly simple, right? But it is actually a massive technical challenge in sharded databases. Why? Because different shards operate completely independently of one another. There is no global clock or universal ordering of writes across the entire system. Fixing this requires complex, deep-level engineering, like designing algorithms that explicitly track causal dependencies in the background, ensuring related writes are processed and served together, or sometimes even forcing all causally related data to live on the exact same shard just to be safe.
Section 5. Designing for lag.
So, what does this all mean for us? The absolutely crucial takeaway from all of this is that eventual consistency is not a free pass to just ignore the user experience.
It requires us to intentionally engineer guarantees based on what our users are actually trying to do. Let's recap. If users are missing their own writes right after submitting them, you absolutely must engineer read-after-write consistency. If your users are refreshing a page and seeing data literally disappear before their eyes, you need monotonic reads to stop time from reversing. And if you are dealing with distributed shards and users are seeing answers before questions, you have to implement consistent prefix reads.
I want to leave you with this final, provocative thought. When you're working with an eventually consistent system, you must always ask yourself, how does this application behave if the replication lag increases to several minutes or even hours? If the answer is a catastrophic, broken experience for your users, then you have to design stronger guarantees into your system from day one. Pretending that your asynchronous replication is actually synchronous, just because it's usually fast, is a total recipe for disaster. You have to design for the lag. It's not a bug, it's a feature of the architecture. Thanks so much for joining me on this explainer, and keep building smarter systems.